Hi students, today I want to discuss about one of the important topic is oscillations. Oscillations. In this topic I will discuss about periodic motion, oscillatory motion, simple harmonic motion, displacement, velocity, acceleration, kinetic energy, potential energy, and the total energy in simple harmonic motion. Okay, so first we talk about periodic motion. So what is periodic motion? The motion which repeats itself in equal intervals of time is called as periodic motion. So we have, the best example is motion of planets around the sun and motion of simple pendulum or motion of a hand's, seconds hand or minutes hand in a watch. So they are all examples for the periodic motion. Now we have the next one is oscillatory motion. So oscillatory motion is nothing but to and fro motion towards a fixed point. Is called as oscillatory motion. So we have the oscillations of a pendulum in a wall clock or the oscillations of a loaded spring. They are all examples for the what you call oscillatory motion. So oscillatory motion may be a periodic, but periodic motion may not be a oscillatory motion. So may or may not. Now, here we have the third type of motion, that is simple harmonic motion. So, what is SHM? Simple harmonic motion. A body is said to be in simple harmonic motion if its acceleration is always towards a fixed point and acceleration is directly proportional to the displacement. That is, A is proportional to X. And it always acts in opposite direction. Then the body is said to be in simple harmonic motion. So mathematically, we can say that A is proportional to minus X implies A is equal to minus Kx, or where K is a constant. Constant we can take it as omega square. So A is equal to minus omega square X. So this is when the body is having any body in SHM, it has an equation. The equation we can say that it obeys A is equal to minus omega square X. So simply we can say that the conditions for the simple harmonic motion. So first condition, the body should have to and fro motion. And the body should be in periodic motion. And also acceleration is directly proportional to displacement. And it should be always towards to a fixed point. And acceleration and displacement must be in opposite directions. Okay? So if a particle satisfies all these conditions, then it is said to be in simple harmonic motion. Okay? So we have, children, two types, that is three types of motions. We can say that periodic motion, oscillatory motion, and also simple harmonic motion. Now, I want to discuss about how is the displacement, velocity and acceleration and kinetic energy, potential energy in simple harmonic motion. Okay. So now here we are considering a particle is moving in a circular path. Let its position initially is at A. After a time t seconds, it has displaced to point P, making an angular displacement at theta. Theta is nothing but the angular displacement. Now we can write this theta. We know that it is nothing but omega into omega t is the formula for the theta. Omega is the angular velocity, t is the time. And let ON is equal to y. And OP is equal to R. So ON is equal to y. And OP is equal to, I am writing it R. Or in some books you can take it as A also. Now, from triangle OPN, we can write sin theta. Sin theta is equal to ON by OP. Or OP is equal to, we can write sin theta is equal to opposite side by OP. So we can write ON is equal to OP sin theta. So OP is nothing but R. So this is equal to R sin theta. And ON is, we have taken that as y. So y is equal to R sin theta is the formula for the displacement of a particle in simple harmonic motion. So we can also write this as theta as it is nothing but R sin omega t also. So if you consider at the mean position, so mean position, so y is equal to 0. It is at rest. At the extreme position, we have y is equal to A. That is R. So y is maximum. So the maximum displacement of the particle is nothing but, we call it as amplitude of the particle. So A is nothing but the amplitude. So amplitude is nothing but the maximum displacement from the mean position. Okay. So now, when we know about the displacement of a particle in simple harmonic motion, now we go for the velocity. Velocity of a particle in a section. So velocity, you can say that rate of change of displacement is nothing but velocity. So we can write it as d by dt of y. So we know that y is nothing but d by dt of y is r sin omega. Just we have. So if you differentiate, that is r into d by dt of sin omega. So we can write it as r into omega into cos omega. So now we can write v is equal to r omega cos omega. So now we know that v is equal to r into omega into cos omega t is nothing but 1 minus sin square omega. Or that we can write it as r omega into root of 1 minus y by r whole square. Okay. So now r omega into root of r square minus y square by r. Cancel the r. Now we have v is equal to omega into root of r square minus y square. So this is the formula for the velocity of a particle at any position in a simple harmonic motion. Now if you want at mean position, then we can write it as at mean position. We know that this we have at any position v is equal to omega into root of r or a, anything we can take. So at mean position y is equal to 0. Therefore v is equal to omega into root a square, or v is equal to omega a or omega r, anything we can take. So at extreme position, we can write it as y is equal to a. Then we can write v is equal to omega into root of a square minus b square. So this becomes g. So velocity is minimum at extreme position and maximum at mean position. Okay. So not only that, when we know about the velocity, now we discuss about the acceleration of a particle in SHM. So acceleration is E. So by definition of acceleration, you know that rate of change of velocity. So d by dt of v. So we know that d by dt of v is r omega cos omega t or a omega cos omega, anything we can do. So you can take a omega, so d by dt of cos omega t. So a omega into, so d by dt of cos omega t, we can write it as this as minus omega sin omega. So this is equal to minus a omega square sin omega. But we know that y is equal to a sin omega. Therefore, this we can write it as omega square into, since we know that y is equal to a sin omega. So we have a is equal to minus omega square y. So again, at mean position, we have at mean position, so y value is 0, y is 0, a is equal to 0. At extreme position, we have y is equal to a, then we can write it as a is equal to minus omega square. So acceleration is max. So students, so acceleration is maximum at extreme position and minimum at mean positions. Okay, so this is minimum at mean position. So when we know that displacement, velocity and the acceleration of a particle in simple harmonic motion, now we go for the kinetic energy. So kinetic energy, we know that kinetic energy K is equal to half m v square. So half m into v So V at any position, we know that omega into root of a square minus y square. So this is equal to half m omega square a square minus y square. So this is equal to half into m into omega square into a square minus y square. This is the formula for the kinetic energy. So kinetic energy of a particle at any position is given by k is equal to half m omega square a square minus y square. Now again we want at mean position. So at mean position we know that displacement is 0, y is equal to 0. Therefore k is equal to half m omega square a square. And at extreme position we have y is equal to a. Then k is equal to 0. So k becomes minimum. So minimum at extreme position and the maximum at mean position. If k is maximum, p will be minimum. If p is maximum, k will be minimum. So now, after knowing this kinetic energy, now we have the potential energy. So potential energy of a particle in a system is given by half m omega square y square. So if it is at a mean position, so we have at mean position y is equal to 0. So then it becomes half m omega square into 0. So this is 0. So P is 0. So at extreme position, we have y is equal to a. So therefore P is equal to half m omega square. So P is maximum. So P is maximum at extreme position. Okay. So when we know the kinetic energy and potential energy, now we go for the total energy. So total energy is sum of P plus K. So P at any position half m omega square y square plus K at any position half m omega square a square minus y square. So we have half m omega square. So minus y square minus I square cancels. So this will be equal to total energy is equal to half m omega square a square. This is the total energy of the particle in simple harmonic motion. So we can also represent it by a graph. So we represent by a graph. We have a graph like this. So this is negative amplitude and positive amplitude, and this is the energy. So this is total energy. It always remains constant. So P is maximum at extreme position. So therefore we will have this curve as P curve, and this is P. So students, now you have an idea for the what we call oscillations introduction. That is periodic motion. Next one is oscillatory motion. Next is simple harmonic motion and conditions for simple harmonic motion. And we have the formulas for the displacement of a particle in SHM, velocity of a particle in SHM, acceleration of a particle in SHM, kinetic energy of a particle in SHM, and the potential energy of a particle in SHM, and finally total energy of a particle in simple harmonic motion. Okay, not only that, we have time period, frequency, and phase of a particle in SH. So here, to remember easily in examinations, so let us say that this is mean position and this is extreme position of a simple pendulum. Alright. So at mean position, y is equal to 0, displacement is 0. And extreme position, displacement is maximum, is nothing but we call it as amplitude. And velocity, so velocity, you know that V maximum is equal to omega square E. So V is V. And third one, kinetic energy is maximum. And kinetic energy is V. Fourth one, potential energy is V. Potential energy is max. So like this, we can say in case of SHM, at which positions, what are the quantities maximum and what are the quantities that are minimum. Okay. And also, when we know this, we know the time period of a pendulum. Our time period is given by E is equal to 2 pi into root of L by G in case of a simple pendulum, and for a loaded spring it is given by 2 pi into root of L by G. So this is for the loaded spring. Okay, so this is regarding the protocol, an introduction to the oscillations. Thank you.